atomic spectra. Now what is this atomic spectra? Okay, so as we know that every element or each element has a characteristic of a spectrum of radiation which it emits. Okay, every element, each element, whichever element you take, it has a characteristic of spectrum of radiation which it emits. So when an atomic gas or a vapor is excited at a low pressure, then we can observe that some radiations are going to be emitted, and those radiations which are emitted, they are in the form of a spectrum. Okay, so we are having a spectral series. We get a spectral series. So this is what every element, if you take any element, each element has a characteristic of spectrum of radiation. Okay, so such emission of spectrum of radiation is called as there is a line emission spectrum, which is called as a line emission spectrum. Okay, we can observe that if you take for example, if you take a hydrogen is the simplest atom. Okay, so its spectrum is in the form of getting line emission spectrum like this. Okay, with the decreasing, so with the decreasing wavelength we will be getting. Okay, so it means so first line spectrum, it will be having a wavelength of 656, next 400, 456, next 450, like so we will be getting an example. I am telling you for an example. If you take any element, then its emission of its spectrum of radiation is going to form in the form of a spectral series. You will be getting a number of series with a decreasing wavelength. So each spectrum, each line spectrum will be having a space between them. Okay, so such spectrum is called as a line emission spectrum. Okay, हर कोई एलिमेंट को अगर हम कोई एक एटॉमिक गैस या तो वेपर को हम उसे एक्साइट करते हैं अंडर लो प्रेशर, एक्साइटेड विद अंडर लो प्रेशर, then we are going to get a spectrum radiation in the form of like this with the decreasing wavelength. Okay, each line spectrum will be having a particular wavelength. Understood? So this is what called as a atomic spectra, or also it is called as a line emission spectrum. Okay, so next topic is there is electron orbits. Electron orbits. Electron orbits. Electron orbits. So here we are finding the total energy of the orbit we are finding. Okay. Now, as we know that in Rutherford atomic model, we came to know that an atom is a electrically neutral charge. It is a electrically neutral charge, right? And that atom consists of a positively charged nucleus. Okay, at the center of the atom, as we discussed in the Rutherford atomic model, according to the Rutherford atomic model, we said that at the center of the atom we are having a nucleus, a small positively charged nucleus. It is called as a nucleus, and around the nucleus electrons are going to be revolved in a stable orbit. So electrons are going to revolve around the nucleus in a stable orbit. So this is according to the Rutherford atomic model. So the centripetal force must be required for the electron to revolve around the nucleus. So to revolve this electron, as we know that electron is a negatively charged particle, to revolve this electron around the nucleus, this is called as nucleus. To revolve this electron around the nucleus, a centripetal force must be required. The centripetal force required to keep the electron revolving around the nucleus. Okay. So that centripetal force will be given by Fc is equal to mv square by r. Here r is the radius of the radius. Here r is the radius. That is from nucleus to the electron. This distance is called as the radius here. mv square divided by mv square. Sorry, mv square divided by r. Here this Fc indicates the centripetal force. That C is nothing but what? Centripetal force. Okay. And also the electrostatic force between the electron and the nucleus is given by Fe is equal to, here Fe is nothing but what? E means electrostatic force between the electron and the nucleus. Okay, electron and the nucleus is given by 1 by 4 pi epsilon naught. That is product of the two charges, that is E square, that is E square divided by, that is R square. Understood? So there is the centripetal force is equal to mv square divided by r, and F is equal to 1 by 4 by epsilon T square divided by r. Okay. Now dear students, so let us consider these other two equations, equation 1 and equation 2. Okay. Now here, this is called as a centripetal force, which keeps the electron to revolve around the nucleus, and Fe is the electrostatic force between the electron and the nucleus. Since Fc is equal to Fe, okay, why we are taking this centripetal force is equal to the electrostatic force? Because to revolve this electron in its stable orbit, these two forces must be always equal. Then only the electron is going to revolve around the nucleus in its stable orbit. So Fc is equal to mv square divided by r equal to 1 by 4 pi epsilon naught E square divided by r. Right. Now we can also write this as mv square equal to 1 by 4 pi epsilon naught E square r. It is r square, no? E square divided by r square. This r will get cancels. mv square is equal to 1 by 4 pi epsilon naught E square divided by r. Consider this as equation number 3. Now this is what mv square is equal to 1 by 4 pi epsilon T square divided by r. Now the kinetic energy of the electron here, which is revolving around the nucleus, its kinetic energy is given by, as we know that kinetic energy of the electron is given by K equal to, as we know that kinetic energy equation, it is given by K equal to half mv square. So half, here I can replace this mv square as 1 by 4 pi epsilon t square divided by r. So it can be written as 1 by 4 pi epsilon naught e square divided by r. So I am writing here from equation 3. From equation 3. So the kinetic energy of the electron is given by, that is K equal to 1 by 8 pi, as 2 4s are 8, that is 8 pi epsilon naught e square divided by r. Now take this as equation number 4 here. Now next we will be having is the potential energy of the electron. Potential energy of the electron is given by, that is U equal to half, 1 by 4 pi epsilon naught, as 1 by 4 pi epsilon naught into E into minus E divided by R. So U is equal to 1 by 4 pi epsilon naught, that is minus, I am writing this minus here, E square divided by R. So consider this as equation number 5. So this is the potential energy of the electron, and this is the kinetic energy of the electron. Now, so what we need to find out? We need to find out the total kinetic energy of the electron in an orbit, in a stable orbit. So therefore, the total energy of the electron is, it is here I am writing here, this total energy is equal to sum of the kinetic energy plus potential energy. So what is the kinetic energy here? 1 by 8 pi epsilon naught E square divided by R. Here it is plus and here it is minus, so therefore I am writing here minus. There is 1 by 4 pi epsilon naught E square divided by R. So therefore the total energy is equal to, as here the estimate becomes 8 pi epsilon r, and here it becomes 2 4s are 8. That is, I am getting, that is minus, that is E square will be getting. So which can be written as total kinetic energy is equal to 1 by 8 pi epsilon naught into minus E square divided by R. So which is the total kinetic energy of the electron in an orbit, that is 1 by 8 pi epsilon naught. So here I am taking this as a LCM here. Okay, so 8 pi epsilon, so I am writing LCM here. Oh, that is 8 4. So 2 4s are 2 2s are 2 2s are 2 1s are 2 1s are. So I am getting here 8 as LCM. So 8 1s are 8, and I am getting here 8 1s are 8, and here 4 2s are 8 here. So that's why I am getting here E square. I am writing this almost up here, 8 pi epsilon naught R into E square minus 2 E square. So which will be getting E square minus 2 E square, again we will be getting minus E square. So total energy can be written as 1 by 8 pi epsilon minus E square divided by R here. So which is the total energy of the electron in a stable orbit. Here we are having a negative sign here. This implies that the electron is bounded to the nucleus. The electron is bonded to the nucleus. So this implies a negative sign. Okay. So this is what the total energy of the electron in an orbit, which is also called as electron orbit. So which is very important. So dear students, just to practice this derivation, take it as a homework. Practice it for 5 times, because this derivation can be asked in an exam also. So for 5 marks or for 3 marks, derive an expression for the total energy of the electron in the orbit. The question they might ask you that derive an expression for the total energy of the electron in the orbit. Okay. Today we will stop here. In the next class we will discuss with a new topic. Thank you.